Okay, so great, 20 years ago I swore I would never ever give a course on Shimura varieties, and here we are. I'm not thanking you. Yes, wait, he's not here. I was asked to tell you that Shimura varieties are out of date. Nobody cares about Shimura varieties anymore. That's from my advisor, by the way. Last time I heard a talk where somebody said that Shimura varieties are useless now. It was maybe 2 years before Scholz's big torsion in the cohomology of Shimura varieties paper. So take that with a grain of salt. Anyway, right. What else did I want to? I don't think I have any more stupid jokes. So let's start. Okay. Oh yeah, the notes. So there are some notes on. Yeah, I'm not really. I mean, the notes are divided into lectures, but I make no promises as to the division of the actual lectures. So, for example, here I'm going to start with something that is actually in lecture 3 of the notes. Okay, so I'm going to try to motivate a little bit the definition of Shimura varieties and why. So if you care about automorphic representations, explain why you should care about Shimura varieties. So this is and by the way, this is not historical at all. I mean, I'm not claiming this is the definition that this is the reason that people introduce Shimura varieties. I'm just saying this is one way to explain why you can care about Shimura varieties. So Matsushima's formula. So what is this? Right. Oh, also I didn't really get the memo about assuming Corvallis. So everything I'm going to say today, I think was probably already known in Corvallis' time. Sorry. So let's take a connected reductive group over Q, G, right. So of course you all want me to say that imagine that G is GLN. Unfortunately, this is not going to work so well for Shimura varieties, as we will discover in a short while. But you can think that G is GL2 if you want, but not GL3. And let's take K infinity, a maximal compact subgroup, modulo center. I pretend G is semi-simple if it makes you feel better. You're not going to lose much at this point. And then this quotient X is a symmetric space. So it's a nice Riemannian manifold. And then what Matsushima did. Oh, maybe I should start dividing my board, otherwise I'm going to run out of board. Oh, well, maybe I should say a little bit more before talking about. So if I have gamma in the Q points, that is an arithmetic subgroup. So what is an arithmetic subgroup? Basically, is G of Z. Of course, G of Z is not well defined. It depends on an embedding of G into GLN. So what it actually means, it's a gamma that is commensurable with some choice of G of Z, and then that does not depend on the choice. But if you're working with GL2, think like finite index subgroup in GL2 of Z. Then you can look at this quotient. So this is what is called a locally symmetric space. Okay, so here I should assume if I want this to be really nice, I should assume that gamma is torsion-free. But which is always true if gamma is small enough. Okay, and so Matsushima, he proved some theorems about the cohomology of these things in the case where they are compact. So I should tell you when these are compact. So this, of course, well, okay, no, I'm not in the semi-simple case, so if G semi-simple is the same as saying that G of R of gamma is compact, if G is reductive, then you have to quotient by the center. Okay, doesn't matter. But anyway, so this space is compact. These spaces are compact if and only if G is anisotropic modulo the center. So that means that there is no non-trivial parabolic subgroup. Well, no proper parabolic subgroup. So here already you see, well, okay, so if you want an example of that, so we want an example that is not trivial. So we don't want G of R to be anisotropic, but we want G to be anisotropic over Q. So what could you do? For example, you could take the invertible elements in a division algebra over Q. Okay, unfortunately, we are going to, that is very nice. That's an enum form of GLN. We're going to have to abandon that very soon too. But we are on the right path. Okay, then Matsushima. I'm not going to state his original result because I'm going to state a reformulation in 5 minutes, but what he did, and he related the Betti numbers of this to automorphic forms on G of R. Well, I should say Matsushima, he worked with semi-simple groups, but okay. So when this is compact. Okay, so if you want to go and read his paper, I put a reference in the notes. But I want to talk about, now we're doing automorphic forms not on G of R, but on G of A. So I want to talk about the Adelic reformulation of this. Okay, and here I feel very silly because I actually came prepared to define the Adels. And, well, okay, so what are the Adels? So it's the restricted product of all completions of Q, which means, families here that are in ZP for almost all prime numbers P, and there's no condition at R. So this is also the product of R by what is called the finite Adels. Oh, finite Adels. Oh, okay. Okay. Well, finite Adels is just this thing. So this is a locally compact topological ring. Okay. And now I'm going to introduce, well, L2 of G. So which we already saw in Eras's talk, which that's good. So it's L2 of this quotient with the action of G given by right translations, where AG, so apparently there is some ambiguity on what AG is. So let me fix an AG. So if SG is the split center of G, then AG is just the coordinate component in Hg of R. So you can forget this. Hg is just here to make sure that this quotient has finite volume. And yeah, I am taking a trivial character on Hg, sue me. I mean, for simplicity, okay? Okay, so this is a very nice Hilbert space, and it has an action of G of A. And so we say that, so we define pi G to be, so what is called a set of discrete automorphic representations of G. And so this is by definition the reducible representations pi of G that are direct factors of L2G. And then I have m pi, which is just the multiplicity of pi in L2G. Okay, so now we know what automorphic representations are. Well, that was easy. So let's go back to the, okay, this board kind of sucks. Let's go back to the co-compact case. Oh yes, sorry, I mean, I didn't say I choose a Haar measure on G of A. Okay, so they are all proportional to each other, so this doesn't change anything. Okay, so assume that G over ZG is anisotropic. Then, well, so then this quotient is compact, and then in that case, this L2 space, so we spent all this time talking about Eisenstein series this morning, forget everything, because I'm in the case where there are no Eisenstein series, and the L2 space just decomposes discretely. So L2G is as a representation of G of A, decomposes into a Hilbert sum over all pi in pi G of pi, appearing with multiplicity m pi. Okay, so all these automorphic representations are also cuspidal, of course, because there are no parabolics. Okay, and then Matsushima. So I tried to track down the first appearance of this. The earliest one I found is in a paper of Arthur, where he just refers to the formula, the non-adelic formula, and says that this follows trivially. So okay, so let's say this follows trivially from Matsushima's work. So under the same hypothesis. Oh, yeah, I forgot to introduce something, but that's okay because I left myself some space. So, adelic locally symmetric spaces. So the geometric object, we're not going to use this gamma under X, we're just going to use a slight adelic variant, which I'll call MK. So MK is this thing. Okay, is open compact subgroup of the finite adelic points. Okay, well, I have to erase my theorem because I really have more to say about MK. Damn it. Okay, so this looks like a different beast if you have never seen this before, but actually it's basically the same object. So I put the parentheses like that to indicate that, so here, K acts by right translation on G of AF. Here, G of Q acts on both factors just by left multiplication. So it acts diagonally. Okay, so this MK is actually a disjoint union of spaces like this. So if I write G of AF as a finite disjoint union of double classes like this, then MK is just the disjoint union of the gamma I under X, with gamma I being equal to Xi K Xi minus 1 intersected with G of Q. So the open compact subgroup of G of AF is like the adelic version of arithmetic subgroup of G of Q, if you want. It's a little bit more restricted, but okay. So this is just a finite disjoint union of locally symmetric spaces. If K is small enough, all these gamma I are going to be torsion-free. But now, I mean, what do we win by doing that? Is that if I take the limit over all K of MK, so this is G of Q dividing X cross G of AF. Well, now I have an action of G of AF there. Okay, and so if I look at limit over K of HI of MK, so this is just Betti cohomology with coefficients in C, you want, so I'm going to call that HI. Well, this also has an action of G of AF. Okay. Oh boy. Okay, somebody please give the IHS some money so they can put like motors on this. Wait. Do I have time to, yeah, maybe not. Okay, so what is Matsushima telling me now? So that this HI, so as a G of AF representation, okay, so I should say I have in my notes, but I'm going very slowly, so maybe I'll just tell you without writing it. You can also think about these actions at finite levels. So if you just look at the cohomology of MK with K fixed, this is the K fixed points in this HI. So you have an action not of G of AF, but of something we've already seen, the Hecke algebra at level K. So the algebra of locally, by K invariant functions with compact support on G of AF. So I'm going to give you the limit version, I mean the version for the limit cohomology of Matsushima Serum. Right, so again, so assuming that G is an isotropic modulo center, so let me just write stuff and then I'll explain. Well, I won't explain everything. So if I have pi, this is an irreducible representation of G of A. And G of A, so G of A is a product of G of AF and G of R. And so pi decomposes as a tensor product of representations of these groups here. Okay, this as an action of G of AF. This is an action of G of R. And I forgot the multiplicity. Okay, so here it's telling me, well, it's telling me two things. It's telling me that the only representations of G of AF that appear in HI are the finite parts of automorphic representations. And the second thing is telling me how to calculate their multiplicities. Okay, so their multiplicities are given by the product of the multiplicity of the pi in L2 of G, and then some GK cohomology group. So I'm not going to define the GK cohomology group. So here G is the Lie algebra of G of R. So this is going to select some infinite parts of automorphic representations. Quite a strong condition on pi infinity, actually, to have non-trivial GK cohomology. So I'm just going to say this is computable invariant in theory. Okay. Or if you want to see there is a finite level version of this. So as modules and under the Hecke algebra at level k, well, it's the same. It's exactly the same formula, except here you have to take k invariant vectors in the pi f part. Okay. Okay, so also, well, I should write less. So here I'm talking about the co-compact case. I should remark that, well, I was told that I can concentrate on the co-compact case. There is a generalization of this due to Morel and Castleman to some non-compact locally symmetric spaces under a condition that is going to be satisfied for Shimura varieties anyway, which is the fact that G of R has a discrete series, basically. Where the right-hand side is the same, but here you have to use another cohomology theory, which is L2 cohomology. I'm telling you that because I'm going to use examples that are not always co-compact, so everything generalizes in the appropriate way. Anyway, so that was one piece of motivation. So these locally symmetric spaces are interesting because we can see automorphic representations in their cohomology. Second, well, a second point is, well, second motivation for what we're going to do, if you want, is moduli curves. So what's moduli curves? It's the case where G equals GL2. So already, I mean, GL2 is not an isotropic, but like see previous remark, there's a generalization to GL2 of this. So if G equals GL2, then MK, these varieties MKs are modular curves, not moduli curves. I'm anticipating. Modular curves. The modular curves, so they are moduli spaces of elliptic curves. Plus some extra structures. And as such, MK are actually algebraic varieties. So, algebraic varieties. And even define over Q. Okay, so yes, I am. I should say MK is the set of complex points of an algebraic variety defined over Q. I am not saying that. Sorry. And if this thing is an algebraic variety defined over Q, then its cohomology has an action of the absolute Galois group of Q. Okay? Or more, well, to be more precise, we have, here we have the Betti cohomology of Mk, its coefficients in C. It's isomorphic to a Lady cohomology of Mk with coefficients in QL bar. I am choosing an isomorphism between C and QL bar to say that. And this one here, okay, I'm going to put the limit over K. This one here is an action. So it has an action of the absolute Galois group of Q, and it still has an action of G of AF. Okay, why does it have an action of G of AF? It's because, so you, right. Well, basically, you can descend all these MKs to algebraic varieties over Q, and also the action of G of AF is by what is called Hecke correspondences. They will also all descend to morphisms of algebraic varieties over Q, which is quite an important point, which I'm just like pushing under the rug here. But and because the action of G of AF is defined over Q, the action on cohomology will commute with this action of the absolute Galois group of Q. Okay. If you want to go at finite levels, you can also define a Hecke algebra over Q, and okay, it's in the notes. And then well, if you have an automorphic representation coming from a modular form, then if you're looking at in H1 of this thing, if you look at the pi f isotypical component, then this is going to be, well, something that I can call sigma of pi. So this is a representation of the absolute Galois group of Q. It's dimension 2, and it's actually, so this, I guess, Sorry, was there a question? In here. Was at least started by Lyon, and it's actually going to be, well, the representation that is supposed to correspond to pi by the global Langlands correspondence. That means that you can check that at every place. If you restrict the sigma of pi to a local Galois group, it's going to correspond to pi, to the component of pi at that place by the local Langlands correspondence. Okay, so yes.
Which local Langlands correspondence you are referring to? Is there a twist or not?
I have no. Please don't ask me that question. I don't. I didn't check. I mean, like basically, first. The only one that I really understand is the unramified local Langlands correspondence. So like there is like an equality between like the Hecke eigenvalues of pi at an unramified place and the Frobenius eigenvalues of this sigma pi, which I can write down, but I don't know if that means that there is a twist. Well, okay. If somebody knows, please like. Oh,
I guess the question is...
Sorry, I forgot to repeat the question. Yeah, I was asked how the local Langlands correspondence is normalized. And I said, like, I don't really know.
You need a twist to have the correct weight.
Okay, you need a twist. Okay, great. I don't know which twist, though. Yeah, but so the point I want to make is like totally independent on whether there is a twist or not. So the first point we had was like, in the cohomology of these things, we see automorphic representations. A second point is like, when these things happen to be algebraic varieties, then in the cohomology, we don't just see automorphic representations, we see something that looks like the global Langlands correspondence, normalized in an appropriate way. And so now the question, of course, is like this is GL2. It's very nice. Is there a more general picture for other groups, for the reductive groups? Okay. So that's two questions. I mean, one or two questions. I'm going to divide it into two. So the first question is, when is gamma under X or MK an algebraic variety? Over C. And the second question is, well, when it is, can we descend it to Q or another number field? I guess those are the questions for today and tomorrow, and the question for Wednesday is when it is an algebraic variety and we can descend it to a number field, can we generalize this picture about the cohomology? Okay. Which I forgot the order of my boards. And in question two, of course, there is the question of in general, a priori, even if the algebraic variety is defined over a number field, there could be several ways to define it over a number field. So can we have a nice way to define it? In particular, we would like this action, as in the GL2 case, we would like the action of G of AF to also descend to the number field. Okay. Otherwise, this is kind of useless. So let's see. So can I answer question one? Oh, here's a blank page. Interesting. Oh, and to spoil what I'm going to say, so Shimura varieties, basically there are going to be these MKs that are algebraic varieties, modulo some technicalities. Okay. Yes?
Do the Hecke correspondences automatically algebraize if
yeah, I'm going to talk about that. Yeah, they automatically algebraize if this is an algebraic variety. Okay, so the answer to one. So I said this X. So this X, I mean, remember it's basically G of R divided by a maximal compact subgroup. So this is what is called a symmetric space. So it has a Hermitian metric where G of R acts by isometries, and there is a what's it called? A symmetry around every point. Okay, so what we say? So we say that X. So what we want to know is when does X satisfy the same kind of conditions, but the complex version of those conditions. So we say that X is a Hermitian symmetric domain. So I'm going to abbreviate by HSD if X has a complex structure and a Hermitian metric such that G of R acts by holomorphic isometries. So it's just so Hermitian metric is just the analog of a Riemannian metric, but just now the tangent spaces of X are C vector spaces. So we want to give a Hermitian scalar product on each of them that varies holomorphically. Okay, so basic example of that is, well, the basic example is the Poincaré upper half plane, but let's do a higher dimensional example. So the Poincaré upper half space. So D is a positive integer, and this is HD plus. So this is the set of D by D complex matrices that are symmetric and such that the imaginary part of the matrix is positive definite. Okay, so this is a D by D real matrix and it's symmetric, so it makes sense to us that it's positive definite. Okay, and if D equals 1, you just get the Poincaré upper half space, the complex numbers with positive imaginary part. Okay, so here you have an action of sp2 of R, sp2d of R. So what is sp2d? sp2d is the symplectic group of, well, choose your favorite symplectic form. So I'm going to use the symplectic form that is just 0 identity minus identity 0. Okay, so this is a group scheme is defined over Z. And usually I choose the anti-diagonal symplectic form because it's easier to write the parabolic subgroups. But here I'm not going to talk about compactification, so it doesn't matter. Of course, all perfect symplectic pairings over Z to D are equivalent. So how does this act? Well, I mean, if you know how, by the way, if D equals 1, this is just SL2. You can just check that this gives you SL2. So if you know how SL2 acts on the Poincaré upper half plane, well, this is the same. It's the same formula. So AX plus B times CX plus D minus 1. Except now A, B, C, D, and X are all D by D matrices. Okay, so for an exercise, check that this is indeed an action. This is transitive. So if you don't want to do the fun exercise because you don't think it's fun, I understand. In the notes, there is a reference to Siegel's paper where he proves all this. And yeah, this was actually proved in a paper by Siegel, and it's pretty readable, actually. So,
sorry, Sophie.
Yeah.
Inverse limit formula? You're about to hear?
Yes.
You have to, in general, have to do something where you like modify the closure, like Q points at the center.
Maybe. Just take a semi-simple group. Yeah. Let's erase this, and then when I rewrite the notes, I can worry about that. Right, okay, so this is the action. And then, okay, so what am I doing? I mean, I wrote some like random, this is an open subset of the C vector space of symmetric matrices. So I wrote some random domain in the C vector space. So first I'm going to express it as one of these quotients, G of R over K infinity. So that's what I'm doing now. Here I have my G of R. Now I just need my K infinity, which is just going to be, of course, the stabilizer of a point. So let K infinity be the stabilizer of, well, what point should I take? I mean, if you know the theory of modular curves, you know I should take I. So let's take I times identity. And this you can check quite easily that it's just the intersection of sp2d of R with the orthogonal group, so it is a maximal compact subgroup in sp2d of R. It's actually also isomorphic to the unitary group by some formula that is in the notes. And so this HD plus as a real manifold is just sp2d of R divided by k infinity. Okay, now where is the, but note that this has a complex structure and that sp2d of R does act by holomorphic maps. Now, where is the Hermitian metric coming from? It's coming from what we call the bounded realization. So the bounded realization is, well, okay, so anticipating a bit. This is a domain in the C vector space. But it's not a bounded domain, obviously. So the bounded realization, we're going to realize this as a bounded domain in actually the same C vector space. And why are we doing that? Because on bounded domains in C vector spaces, we have what is called the Bergman metric. So this is isomorphic to, what I'm going to call D of D. So this is the set of symmetric matrices in MD of C such that identity minus x star x, which is the correct, I think, yes. Yeah, is positive definite. Right, so this is still an open subset of the finite dimensional C vector space of symmetric matrices, but now it's bounded. What is the, well, I mean, it's like, if D equals 1, this is basically the unique disk, the open unit disk. Okay, so what do? You send x to, so you send x to I minus x over I plus x. Okay, so I minus x divided by I plus x. Easy, okay? And then the map in the other direction is almost the same formula, again, in the notes. And now this one here, it has what's called the Bergman. So every bounded domain in a finite dimensional C vector space has a canonical, up to a positive number, canonical metric called the Bergman metric, which, I mean, you can write the formula in this case. Again, it's in the notes, probably, maybe there's a mistake in it, I'm not sure, but there's also a reference to the Siegel paper where he calculates it. And the Bergman metric being canonical is invariant under every holomorphic diffeomorphism of this. So if I transport it back here, it's going to be invariant under the action of sp2d of R. So that gives me the structure of Hermitian symmetric domain. Okay. So now let's look at the general. So this was like proof that Hermitian symmetric domains do exist. And actually, they are all classified. So here's the theorem. Right. So suppose that so just to simplify my life, I'm going to suppose that G of R is adjoint and connected. You can always reduce to that case, because in that case, G of R is just going to be the group of the automorphisms of X. Okay, and then X is a Hermitian symmetric domain if and only if there exists a morphism of Lie groups, so U from U of 1 to G of R, satisfying the following conditions. So A is that, well, U is minuscule, so that means that the characters of U of 1 in the Lie algebra of G of C, where the action, of course, is by adjoint action times U. Well, they are all the only characters of U of 1 that appear in this Lie algebra are 1, Z, and Z minus 1. Okay. And the second condition is U of I is a Cartan evolution. Of G of R. So what this means, sorry, not U of I, conjugation by U of I. So int U of I. So that means that if I look at the group of elements in G of C, such that G equals U of I transpose G U of I minus 1, this is compact. All right, I think that's, no, not transpose G, G bar. Transpose G doesn't make sense. You can tell me when I write something that doesn't make sense. G bar is just, I mean, it's just complex conjugation on all coefficients you want. So this is actually going to be a compact inner form of G of R. So this condition implies that G of R has a compact inner form. And then, well, okay, I don't. So in my reference, there is a condition C that says that U of I is not trivial on any factor of G of R, but as seems to be implied by conditions A and B. So, well, by condition B at least, because like, how could you be a Cartan evolution if you've trivial, unless the factor is compact? But if it's compact, then it doesn't count in X. So. Anyway, so let's just stay with that. Moreover, we may assume, so you can choose U such that K infinity is like this the centralizer of U. And then X is just going to be, well, the GR conjugates class of U. So the set of GR conjugates of U. Okay, so, well, I'm not going to give, so in the notes there is some very quick explanation of how to construct U when X is a Hermitian symmetric domain. But maybe I'm hoping to add something about the other direction someday, but okay. Yes, question? Or no? So in our example, okay, so maybe SP2D is not a joint, so maybe take G equals PSP2D, doesn't change the symmetric space. Then what is U? You can take this one. Okay, and then, well, this is a very strong condition on G of R. So for example, if G is PGL3 or PGLN for n at least 3, well, you can check that there is no Cartan involution. Or, yeah, so exercise if you want. So the remark, yes, so the G of R having such a U, I will classify. So if, there are nodes of Milnor introduction to Shimura Varieties, where he gives the full classification of all the the real semi-simple Lie groups that can appear. So, for example, in type A, so the factors of type A of G of R, you cannot have GLN. You can only have unitary groups. PSU, PQ. And you cannot have any factors of types G2, F4, or E8. Okay. So, so those are only examples. I mean, you have a list of all the possible adjoint real Lie groups that can appear here. Adjoint semi-simple real Lie groups. So, I mean, here we saw that you can have simplicity types. There's also some orthogonal groups that appear. So you can have some groups of types B and D, which is well. I don't want to say unfortunately because those are quite interesting, but they are very scary to me. The orthogonal type Shimura varieties. Anyway. So that's the start. And now let's finish the answer to 1. So that's, yeah. Oh, although I realized while preparing this talk that I gave a reference to Milner's notes for the theorem, and I forgot to check who proved it first. So I'll find out and add it in the notes, but if anybody knows. Here? No? I mean, I don't know, Siegel, Satake, I mean, Morel. Well. The next theorem, I know who proved it. It's Bailey-Borel and then Borel for some part of it. So if X is a Hermitian symmetric domain, then for every gamma, so an arithmetic subgroup of G of Q, this quotient gamma under X is well, has a unique structure of quasi-projective algebraic variety over C. Okay, so what Bailey-Borel did is that they constructed an open Abelian of this into a projective algebraic variety called the Bailey-Borel compactification or minimal Satake compactification or minimal compactification or Bailey-Borel Satake compactification. And what Borel proved, he proved that, well, the upshot of what he proved is that if you have an algebraic variety over C, any holomorphic map of this algebraic variety into one of these, gamma under X, is automatically a rational map. Okay, so this is very strong. So in particular, the structure is unique, but this also implies that all Hecke correspondences are algebraic.
You have no condition on gamma.
Well, if I want it to be smooth, I need gamma to be torsion-free. But if gamma is not torsion-free, then this is just a singular, well, an algebraic variety with some like pretty mild singularities.
It's just adding open compact subs.
Well, here it's an algebraic group, but like if I want to do the Adelic version, then I will say for every open compact subgroup K of G of AF, then MK has a unique structure of complex algebraic variety and is quasi-projective. And because if gamma is not torsion-free, I can always go to a subgroup that is torsion-free, then like a gamma prime in gamma that is torsion-free, then X over gamma prime is a smooth quasi-projective algebraic variety, and then X over gamma is a quotient of this smooth projective variety by a smooth quasi-projective variety by a finite group. So, right. Okay.
Hi, sorry, would you mind repeating what are the maps that are automatically rational?
Yeah, so every time I have... sorry, yes. So I was asked to repeat, well, yeah, what are the maps that are rational? But okay, the question is contained in the answer in a way. But okay, so I mean the uniqueness property. So what did Morel prove? He proved that every time you have an algebraic variety over C and a holomorphic map from this algebraic variety into this quotient, then this holomorphic map is rational. Okay, so I think he proved it for smooth algebraic varieties, but by resolution of singularities, then it's true for all algebraic varieties. And yeah, I mean the idea is, well, I mean, okay, no, I don't have time for that. Sorry. Right. So let's see. What can I do? So maybe if I'm at peace with not formally introducing Shimura varieties today, I can talk about this. Yeah. Okay, so I want to talk about an important example, which, so we finished question 1. So we know, okay, we basically know which one of these are going to be algebraic varieties. So it depends, it's some condition on G of R. Okay, but now the question is, we don't just want them to be algebraic varieties over C, we want to descend them to number fields. So the question is which ones descend to number fields? How do we descend into number fields? Okay, so I just want to do an example that will guide us a little bit. The example is the Siegel modular varieties. So Siegel modular varieties is so it's a generalization, higher dimensional generalization of modular curves. So modular curves, so the modular curves is the case of GL2, and what happens with modular curves is the Siegel upper half plane basically parameterizes elliptic curves over C. Okay, so a natural question is like, can we do something similar with Abelian varieties of a higher dimension over C? Okay, so let's talk about Abelian varieties over C. So let's take A. AV means Abelian variety. Over C of dimension D, and D is going to be fixed. Okay, well, an Abelian variety over C in particular, it's a connected compact Lie group. So its Lie algebra is, the exponential map is a universal cover. So A is isomorphic to Lie of A divided by some lattice lambda. Well, Lie of A is a commutative complex Lie algebra, which is just isomorphic to C to the D, and lambda is pi1 of A, which is also because A, well, which is also H1 of A with coefficients inside. Okay, and then so it's starting pretty well. All the Abelian varieties are quotients of C to the D by some lattice. Unlike the case of elliptic curves, not all quotients of C to the D by lattices are going to be algebraic. Okay, so we need another condition, which is we need a polarization on the lattice. So let's talk about that. So in this picture, so the dual Abelian variety, well, I mean, it's just Lie of A dual over some lambda dual. Well, what is Lie of A dual can be identified with the set of semilinear forms on Lie of A. And with that identification, lambda dual is the set of, so if the forms are called L, is the set of L such that the imaginary part of L takes integer values on lambda. Okay, so all that you can find in Mumford's book. Precise references in the notes. And then, so a polarization. So polarizations are going to be in 1-1 correspondence with positive definite Hermitian forms. H on the Lie algebra, such that the imaginary part of H takes integer values on lambda. And what is the, if I have H, what is lambda H? Lambda H sends V in Lie of A to the semi-linear form here.
No, it's not on the algebra of A, Sophie, it's on the H1.
What?
It's not an Hermitian form on the Lie algebra. Oh, okay, it's okay. Bon.
Yes, it is. Right. So when you have a polarization, it also gives you what is called the Vel pairing. So psi lambda H. Okay, so this bracket n means n torsion points. So here the Abelian varieties are over C, so I'm just identifying them with their C points. So this is n torsion points in the C points. In general, that would be the subscheme of n torsion in A, if A is an Abelian scheme. Okay, so here I can go from AN cross AN to AN cross AHN, and here I have a canonical pairing landing in mu n, here mu n of C. And so what is it? So you stand VW2 exponential of minus 2 pi I n HVW. Okay, so you can check that this is, so AN is just 1 over n lambda divided by lambda. So this is the correct factor, so that this will only depend on the classes of V and W modulo lambda. I'm pretty sure. You also get, well, okay, or note that we are over C, so the polarization also gives a symplectic pairing on lambda, which is just, well, imaginary part of H. Okay, so now I'm just going to, I'm just going to give you the result. So the result is that this point carrier per half plane, per half space, sorry, is in bijection with the set of isomorphism classes of triples A, lambda, eta, where, well, A is an Abelian variety over C of dimension D. Lambda is a principal polarization. So it means a polarization that is an isomorphism. And eta eta, so it goes from H1 AZ to Z to the 2D is a symplectic isomorphism. Okay, so here, here I have a symplectic form given by the polarization, and here I have the standard symplectic form with the same metrics as the one I used before. 0 identity minus identity 0. Okay, and what is the map? Of course you can use your favorite symplectic form if you want. You just need to change all my formulas. It's like if I have x in HD plus, I send it to, well, ax, lambda x, eta x, ax. So it's c to the d divided by some lattice. And again, like if you know, this is just generalizing the result for d equals 1. So the lattice should just be, well, z plus zx, right? I mean, so it's z to the d plus x z to the d. Lambda x is lambda of hx, where hx is, well, so it's the Hermitian form with matrix imaginary part of x minus 1. And we know that imaginary part of x is positive definite. And eta, well, what is h1 of az? I mean, what is the lambda x? It's lambda. This is the lattice. So we want an isomorphism of that with z to the 2d. So basically, well, we send ei to ei, and we send xei to ei plus d, I between 1 and d. Okay, like the only reasonable thing. Right? Okay, so this is, I mean, there are a few more details about this in the notes, like how you get to that kind of formula. But basically, like showing that every lambda eta is of that form is the easier part, and the more the meat is in the fact that this formula does define an abelian variety and not just a complex torus. So of course, this is because we have the polarization, and then you use something like, for example, the Kodaira embedding theorem to show that the polarization does define a projective embedding of this. Okay. But anyway, once we have this, aha.
Quite over time.
I am not over time. I started at 30. Oh no, you're right. I am over time. I don't know. It's kind of. Can I state the corollary or not?
Well, maybe you can recall this proposition and state it further.
Yeah. Okay. You're the organizer, sir.
All right. Let's thank Sophie for.